So our last chapter, our last work problems, chapter 24. So let's go ahead and do this. As always, we want to get the credits. So credits to chemistry books, textbooks by Brown and LeMay, and also by Zumdahl. And also to, as always, Mr. Mack's AP Chemistry website. The answers here are from the author. Let's go to the next slide. So here are some credits, also McMurray and Fay. Chemistry, and also again to Mr. Max. And again, next slide, answers here provided by myself. Next slide. All right, so what are you likely to see on an exam? This chapter, maybe more than any other, would be confusing. So what you're most likely to see is what you're looking at right now, and that's for both my exam and also for the final exam. However, there are a few other things that you'll probably see, especially on my exam. You'll definitely see some other things. I'll try to point those out as we go through. There are some things that you're less likely to see, like maybe some of the stuff that deals with polymers, certainly some of the stuff that deals with biochemistry. So I would focus on learning how to name and also on isomers. So know the general classification of isomers, which we talked about in the lecture notes, the difference between stereoisomers and structural isomers, and then the difference between enantiomers and diastereomers. So let's go through these together. I'm going to go ahead and get my marker ready here. And let's name these things. We've got several naming problems. These are the ones I would focus on most. So starting here with A, we've got a problem with an alkane that we're supposed to name. So let's just count our carbons. We've got 1, 2, 3, 4, 5, 6 carbons here. So this is going to be a hexane, and it's got 3 side groups. So should we start counting on the left or over here on the right? And the answer is going to be, we want to start on the left because that's going to give us our lower numbers. So if we start on this side, we're going to wind up with 1, 2, and then there's 2 methyl groups, and then we come to 3, 4, 5, 6, and we're at the 4th carbon we had another methyl. So we have hexane with 2, 2, 4 methyl groups. So it's 2, 2, 4 trimethylhexane. Okay, so B, let's count these together. We're going to have to go from this one all the way over to this one. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So in our longest chain, we have 9 carbons. So this is going to be nonane. And then there's one more carbon in here, right here in the middle, that's a methyl group. And it doesn't make any difference where you start, you're going to wind up with 1, 2, 3, 4, 5 methyl nonane. Okay, so you see that? All right, let's go ahead and move to the next one. 1, 2, 3, 4, 5 carbons in the longest chain. It's an alkane, so it's going to be pentane. And it doesn't matter where you go as far as off on those other chains, you're always going to get a maximum of 5 carbons. And we have 4 methyl groups, right? So it's easier if we just let this middle part be the main chain here. So we have 1, 2, 3, 4 methyls stuck on there. So we're going to have a tetramethyl situation here, right? And it doesn't matter again if we start left or right. We're going to get 2, 2, 4, 4 tetramethyl pentane. Okay, next slide. Here are your answers. Next slide. Name each of the following alkenes. All right, so for alkenes, we start off by counting the longest chain, and then we figure out where is the double bond, and we want the lower carbon number of the double bond, and that's going to set the rest of the numbers. So here on A, we have 1, 2, 3, 4 carbons, right? So that's going to be butane, but it's going to be butene because of the double bond. So we've got butene as our base. And then what butene is it? It's 1-butene because the double bond starts at 1, at carbon 1 here. So it's just 1-butene, and there aren't any side groups. So it's just 1-butene. For B, our longest chain has to include the double bond. So 1, 2, 3, 4, 5, 6. So this would be hexane if it were an alkane. If it's hexene, and we want it to be 2-hexene, not 4, because we want the number here for the double bond to be low. So it starts at carbon 2. So it's 2-hexene, and then we do have a side group here. It's a methyl, and it is on carbon 1, 2, 3, 4. And again, this isn't up for deliberation here. This carbon has to be carbon 4, because when you decide that this is carbon 2, because of the double bond being here, then that sets everything else. So it's 4-methyl 2-hexene. And then for C, we have, let's see, it doesn't matter whether we start over there or not. So 1, 2, 3, 4, 5, 6, 7 looks like it's going to be our longest chain right there. So we're going to have two side groups, and we're going to have a double bond. So, all right, so if it's 7, then it would be hexane, but we change it to hexene because of the double bond. And it looks like the lowest number would be if we start at this end, so it's 1, 2, 3 hexene. Or let's see, 1, 2, 3, 4, 5. So it would be heptene. Sorry, if I said hex a minute ago, I was wrong. It's hept. 1, 2, 3, 4, 5, 6, 7. Yeah, so it's heptene. And it's going to be 3-heptene because the double bond starts on the third carbon. And then we have 2 methyl groups here. So we have 1 here, and it's going to have to be carbon 2 because we've already set the numbering system when we decided this is 3. Actually, this carbon is 3. So this is going to be carbon 2. So it's 2-methyl, and then 3, 4, 5 methyl here. So this is 2,5-dimethyl 3, and then it's hep, H-E-P-T, ene. Next slide. Next slide. All right, now this one we're supposed to actually draw these out, which I'm not going to do that because it's very clumsy to do with this little marking thing. So I'll just tell you how you would do these. So give the structure for each of the following. 3-hexene. Okay, that one I think you can figure out on your own, right? How many carbons would you draw, and how would you draw them? Well, just draw 6 carbons in a row because it's hex. They're in a row, no branches or side groups, right? And then you would put your double bond between carbon 3 and carbon 4. So that's pretty straightforward, and so we'll see what that looks like in just a moment. All right, for heptadiene in part B, you're going to have 7 carbons. They're all in a row, and then you're going to have 2 double bonds. So if you want, start at the left-hand side and put a double bond between carbon 2 and 3, and that would be one of your double bonds for your diene, and then put another double bond between carbon 4 and 5. And that would be the second. So 2 double bonds, that's the diene part. And then you're finished. And then for C, octene would be 8 carbons. So start by drawing 8 carbons in a row, and then come over to carbon 3, and between carbon 3 and 4, draw your double bond because it's 3-octene. And then using the same numbering system that you used to do that, come to carbon 2 and put a CH3 on it, and you're finished. Next slide. So here are the drawings down here, the structures, and I'll let you look at that at your leisure. Next slide. There is only one compound that is named 1,2-dichloroethane, but there are 2 compounds that can be named 1,2-dichloroethene. So the difference here is that this is an alkane and this is an alkene. So what's the difference? Well, when you have an alkane, you have all single bonds, right? So they're all sp3 hybridized, which means that you can take those bonds and twist them around and around any way you want. When you have a double bond, you can't do that. And we know we have at least one double bond here because of the ethene. So what that means is when you have a double bond, it's rigid. That means you can have cis-trans isomers, or you can call those geometric isomers. So when you have 1,2-dichloroethane, let me try to just sketch this. You have a double bond, and these things are really, really hard to draw with these to get those lines. Can't believe I did it that well. All right, so here's our C double bond C, and it is ethene. So we could have a situation where we could have the chlorine here, and I'm not even going to try to draw this again, but we could have the other chlorine on the right-hand side here or here, and so I just won't draw it. If we have it up here, then we've got a cis situation. If we have it down here, we have a trans situation. They're not the same, they're not superimposable. There's no way that you can twist this around and make them the same, because this bond right here won't rotate, because it's a double bond. It won't rotate. Okay, so that answers that question. Next slide. Here's a picture of it. So here you can see this is the trans situation and this is the cis, where the green things are the chlorines. Next slide. Okay, so on that same note, which of the compounds in exercise 25, which is here, and 27, which is here, which of these can exhibit cis-trans isomerism? So the deal is, to answer this, whenever you've got two things on one side of the double bond that are the same, then you cannot have cis-trans isomerism. So if you look at all of these, we have 6 different choices in the 2 problems. There's only one that has the possibility that it could not have 2 different things, and that would be A here in number 25, right? That's this very first one, because in A, what we have on the left-hand side of that double bond is a carbon, and to that carbon are attached 2 H's. And so it doesn't really matter whether the H that I'm drawing right now is on top or bottom. You're still going to get the same thing, so there's no possible way you can get cis-trans isomerism for this one right here. So we'll put an X by that one, and you can look over the other choices if you want to, but notice here there are 2 different groups here, 2 different groups here, and then come down to C, there's 2 different groups here, 2 different groups here, and then for number 27, the same thing here, and so forth, so all the way down. So for all of the other ones except A and 25, you could have cis-trans isomerism because you have different groups on both sides. Next slide. Next slide. All right, good. Here's a sample problem of when you have to determine functional groups. So in A here, the functional group is actually this thing right here. And there's another one down here, but it's the same thing, so it really doesn't matter. This is still going to be what's called a ketone. So a ketone is when you have C with an R group on both sides, and then you have a double bond to O. So it turns out these C double bond O things come up a lot. B, we have again the C double bond O, but now we have an H beside it. And whenever you have something like that, it's called an aldehyde. So C double bond OH, that group right there is an aldehyde. C double bond OOH is a carboxylic acid. So that would be the answer for C. And then when you have NH2, or on the end of a molecule, it could be NH3, you have an amine. So this one down here at the bottom, D, is an amine. Next slide. Next slide. All right, these are a little more challenging, and I don't think you'll see these on any exam. If you do, it would probably be mine. So A here, this is a ketone. So A and B and C are all named a little bit differently than what we've seen, but it's okay if we go ahead and go through these because it'll help you to understand in case you happen to see these somewhere. So for A, what we want to do is find the longest chain, as we've done in the past, right? So it's going to be 1, 2, 3, 4, 5, 6. Do you agree with that? So 6 carbons mean it's going to have a hex in the front in the root name. And it would be hexane if it were just an alkane, right? But it isn't. And then we've also got this thing right here that we need to worry about, which we're going to do in a moment, and then we've got 2 chlorines. All right, so let's worry about the chlorines last, because they're going to be easy to fix. So if we have a 6 carbon chain that has a ketone in it, which this is, then we name it as follows. If it would be hexane, we call it hexanone. Hexanone, hexanone. And like we have to do in other situations, like with alkenes and alkynes, we have to put a number where the double bond O is. So it's carbon 1, 2, 3. Again, choosing from the side where you're going to get the lowest number. But once again, as soon as we decide that we're going to start here on the right hand side, then that sets it for everything else. So it's going to be a hexanone, and it's going to be a 3-hexanone. Okay, it's a 3-hexanone. And the reason I'm not writing it out is because it takes too long. And then you've got these 2 chlorines. So let's count. So 1, 2, 3, 4, 5. 4 and 5. So we've got 4, 5 dash dichloro dash 3 dash hexanone. Okay, for B, what kind of a group is that? C double bond OH is an aldehyde. So the way that you name those is you count the longest chain. So let's do that. 1, 2, 3, 4, 5. And you've got to get the aldehyde group in that longest chain. So 1, 2, 3, 4, 5 would be pentane. And so when you have an aldehyde, you would think, well, maybe it's pentanaldehyde, but it is actually abbreviated to pentanal, Pentanal. And then you've also got these two methyl groups that you have to deal with. But the main part of the name is pentanal. So that's how you name aldehydes. And then you've got, whenever you've got an aldehyde or an acid, you always count that carbon that has the double bond to the O as 1. So you have 2 and then 3. So if you'll notice here, this carbon 2 is the one that has this methyl, and this carbon right here is the one that has this methyl. So it's going to be 2, 3 dimethyl, and then it's going to be 1, 2, 3, 4, 5. So it's pentanal. So it's 2, 3 dash dimethyl pentanal. And then C is a carboxylic acid, and when you have, oh no, it isn't. I'm sorry, it's not a carboxylic acid. It's an aldehyde. When you have an aldehyde attached to a benzene ring, it's called benzaldehyde. That's just something you just have to memorize. And then we also have a methyl group here. And so again, this carbon right here is actually going to be the number 1 carbon, because we're going to start counting with the carbons on the benzene ring in this case. So even though we would typically start with carbon number 1, where the aldehyde group is, in this case we're not. We're going to start right here. So if we start with this as carbon 1, then we have 1, 2, 3, I'm trying to get this thing to work, 3 methyl, and then it's just benzaldehyde. So it's 3 methyl benzaldehyde, where the benz comes from the fact that this is benzene, and then this is the aldehyde. Next slide. Next slide. Name the following. Okay, this one has the carboxylic acid. So in this case, this is going to be carbon number 1, because it's where the carbon that's attached to the double bond. The only exception would be in the case like where we have benzaldehyde. So here, that is going to be carbon 1. So we need, again, to get the longest chain, and then name this as a carboxylic acid. So 1, 2, 3, 4, 5, 6. I believe that is the longest chain you can get out of that, including the C double bond OOH. So again, this is a carboxylic acid group. So it would be something with, hopefully with acid on the end of it, and it turns out that's correct. So in this particular case, since it's got 6 carbons, it would be hexane if it were an alkane. But with the acid group, you just change it from hexane to hexanoic acid. And then we also have an ethyl group stuck here and a methyl group stuck up here. So we use the same numbering that we had before. When we start with an acid, we let that be carbon 1. So this one right here is carbon 2, and that's the one that has the methyl. And then this one right here is carbon 3, and it's the one that has the ethyl. I'm not sure how I ended up with the answer on the same problem before I actually did it, but anyway. So we're going to have a 3-ethyl and a 2-methyl, and it's going to be hexanoic acid. So the only decision we have to make is to decide whether to put the ethyl first or the methyl first. And so we go back to the rule of alphabetical order. Ethyl comes first and then methyl. So it's going to be 3-ethyl, isn't that right? 1, 2, yeah, 3-ethyl, and then 2-methyl, and then it's going to be hexanoic acid. Next slide. Complete the following reactions. All right, so for the first one, we have a double bond. That can do a lot of things. Again, you'll find out in organic chemistry. So here, if we add H2 with a catalyst like platinum, remember what will happen? The H2 will line up with on the platinum above the double bond and add across the double bond. So you're just going to end up with whatever you would have here if all of these were CH3, CH2, CH2, CH3. In other words, you're going to wind up with butane here. So the answer to this one is just going to be CH3, CH2, CH2, CH3. Which again, because it's so hard to write with this little marker, I'm not even going to try. For B, this one doesn't need a catalyst, so you'll want to try to remember that. Because if it did, and if they just added the CO2, then you wouldn't have any reaction. But in this case, it doesn't need the catalyst. So if you add two Cl2s, one Cl2 can add across this double bond so that you're going to end up with a Cl there and a Cl there, and then also another Cl right there and another Cl right there. So let's see, the total length here is going to be 1, 2, 3, 4, 5, 6. And so you're going to have a methyl group, which I'm not really worried about that too much. So it's going to wind up being actually hexane. And it looks like you're going to wind up with 1, 2, and then 3, 4, 5 tetrachlorohexane. And then you've also got the methyl group here. And then here, when you add Cl2 in the presence of this stuff right here, so again, you have to remember this, the FeCl3 will allow the benzene ring to react, and you'll end up adding a Cl right there. And the H that was there comes off and joins the other Cl over here from the Cl2 and makes HCl. And then for the last one, whenever you've got a O2 with a spark, you're going to burn it. That's referred to as combustion. And so what will happen is it'll just burn all up and produce CO2 and H2O. I'll just write the CO2. So it'll produce CO2 and H2O every time. And then how many CO2s? Well, count the carbons over here. You've got 1, 2, 3, 4, so it will make 4 CO2s. How many H's will it make? Well, count the H's on the left. You've got 3 plus 2 plus 3, so that is 8, so you can make 4 H2O's. And then you just come back and count up how many O's you have total. I'm not going to write that out, but it's 4 H2O. So you'd have 4 O's over here, and you'd have, looks like 8 over here. So it looks like that would wind up being a 6 that would have to go in front of there. Next slide. Next slide. All right, this is an interesting one. When you have toluene, you've got two different things going on. You've got the benzene ring. Remember, the benzene ring only reacts in the presence of that Fe stuff. Whereas when you have something like this up top, remember that that is an alkane. And the way that, one of the ways that we said that that can react is if you shine a light on it and do that in the presence of something like CO2. So that's what they're asking in this problem, but they're asking for both of those situations in the same problem. So they're saying, first of all, if you, let's read it, if you put it in the presence of iron, so I'm reading right up here at the top, if you put this stuff in the presence of iron and also with chlorine gas, what's going to happen? It's going to react down here on the ring, right? And that's what we just said a couple of minutes ago. So you're going to wind up with the Cl adding down here if you do that. But what if you don't do that? What if, instead of doing it that way, what if you put the Cl2 in with the toluene, and then instead of doing it that way, you shine a light, and you'd have to know which type of light to shine. But you do that, what would happen then? Well, in that case, the Cl would do what it did back when we talked about alkanes. It'll add right there, and one of these H's will go onto the other Cl so that this would become CH2 here. Okay, next slide. So this just explains what I just said. So I'll let you pause this and read this if you want to. Let's go to the next slide. All right, how would you synthesize each of the following? 1,2-dibromopropane from propene. So propene is C double bond, which I'll come back and write in the other bond in just a second, and then a single bond and then another C. I'm not going to put the H's on. All right, so there we go. There's propene. Assume that there are H's on all of the C's, the appropriate number of H's. How would we make this? In other words, how would we put a bromine here and a bromine here. Well, all you have to do is just add Br2 to this, it turns out. You don't even need a catalyst, because remember, this is so reactive that you can just add the bromine to it and it will react with no catalyst. So you just, the answer here would just be add Br2 to it, and that's all you have to put. Next slide. Next slide. All right, these polymers can be a little hairy. So what we need here is the monomer for this. So what I'm going to do, I'm just going to go ahead and draw this. So what we need to start off with is a whole bunch of things that look like this. And they've got to have that double bond in there. And then they're going to look like, this is going to have an F up here. And then below also this thing. Just drives me nuts. Okay, and then an F down here. And an F up here. F. I guess if I did this long enough, I'd get good at it. And then a CL down here. I remember when the first time I tried to do a laptop with the little finger thing, you know, not with a mouse, but just using the pad, the finger pad or whatever it's called. I was actually trying to do a really bad time to learn how to do it when you're trying to do your doctoral thesis in front of a group of, you know, people that are like world famous nuclear physicists. And I remember I was just struggling mightily with this silly thing. And, you know, even years later, I'm not that great at it, but I mean, I'm a lot better than I was then. Anyway, you would have to have a whole bunch of these things. And then what you'd need is you'd need to have some way to initiate this, like with a free radical that can come in here on this side and attack the double bond and cause the double bond to flip over and leave a free radical over here. So that would be like an addition polymerization. So it would then attack the next one. Next slide. So it isn't this. This is not the answer. The answer is here. And that is what I just kind of like tried to draw on the previous slide. All right, next slide. And then this one is the other kind of polymerization. So what would you have to have? And again, I've got the answer here, and I don't know how that's happening. So I guess something went wrong. But anyway, so this polymer here, this is actually the monomer. Let's see, what they're asking is draw the structure of the polymer. So if we have a whole bunch of these and they make a polymer, what will it look like? It'll look like this, where the actual chain is actually coming right across here, and I'll try to be careful when I draw this. So all of these are going to line up with this part right here of each one of these monomers next to each other, and they're actually going to attach. So this double bond comes over to this one, and then the next one, and the next one. So that's actually what I just tried to draw up there, is actually this part right here. So that everything that sticks down below the lines that I'm drawing right now, that's going to be the same. That's just this part right here, and that doesn't really change at all. And also this part up here at the top, this CN, doesn't change either. So this part up here stays the way it was. The only thing that changes is the part in the middle, and what's changing here is that double bond right there is becoming a single bond, and it's flipping to the next monomer, which I was trying to draw and it didn't go. Okay, next slide. And then here is another one that has the answer. All right, Kevlar. So what we see here is this is going to be a condensation reaction where the H is going to come off of one side, either here or here, and then the OH off the other side. And you're going to wind up with a situation where you're going to have, over here, you're going to wind up with a C double bonded to the O, and then the O, let's say, left over. So let's just say it's going to go this way. So O double bonded to C, and then the O from this one. And then we'll assume that the H goes along with, oh, let's see, that won't work. Okay, no, never mind. The OH has to come off. So you're going to just have the C here, and then the H here will come off and join with the OH over here. So I need to get rid of that, sorry. So that will be the water, and then that will leave you with the N. So this C would actually come across here and bond to the N on the thing that's on the left, and then of course that N is also bonded to the other H that's still left over, and then that N in turn goes to the ring, and the C on this side also is bonded to a ring there. which I'm not going to draw the whole thing. All right, so when you have a situation like this, so just forget about that thing, right? Just ignore that. So this is called an amide, where you have a C double bond O with an NH. And in this particular case, that's all you'd call it. If you were doing 2 amino acids in a protein, you would also be able to call it a peptide linkage. All right, so the question is, draw a structure of the portion of this chain. Well, we just did that, so we just kind of like can just transfer this right down here. And this thing right here is what we just did. So what happened to the H that was on the NH2 and the OH that was on the COOH? They went together and made a water molecule, and then the water molecule, which isn't shown here, but it would be like you would have plus H2O over here somewhere. So this is called the condensation type of polymerization. And as soon as I finish writing this, we can go to the next slide. Here again are our amino acids. Now what they're going to ask in the next problem, and I'll just go ahead and do it now, is they're going to say, okay, which of these amino acids has an OH? In other words, an alcohol group. So you would just pick out that one, and that one. Okay, so serine, tyrosine, and threonine. And then they're going to do the same thing for some of the other functional groups. And so I can't really flip back and forth. So what I'm going to do is just ask you guys to go ahead and do this on your own. So like, for example, if they were going to ask you which of these have a COOH group or COO minus, in other words, acids, well, those two right there that I'm circling right now at the bottom left, aspartic acid and glutamic acid. And then there are some others that they ask you to do, so I'll let you do that on your own. So let's go to the next slide, and then the next slide. And here are your answers to that. Next slide. All right, so multiple choice. These are from, actually, these are not from Mr. Mack's website. I think that they don't have this on Mr. Mack's website for this chapter, or I don't think they even have it for the nuclear, so I got this from some other source, which it should be referenced. So let's go to the next slide. Yeah, okay, so I got these from Boise State, Chemistry Boise State EDU. Okay. All right, so just to give proper credit to that, what is the IUPAC name for the following compound? Now, this is exactly what you're likely to see on your final. So find your longest chain. So let's do that. So we've got, let's just start right here for the heck of it. Looks like 1, 2, 3, 4, and then 5, right? So you have to go up, even though it isn't drawn straight across, it's still part of that longest chain. So let me just double check. 1, 2, 3, 4, 5. I'm pretty sure that's it. So what do you call a compound that has 5 carbons in a row? It's a pentane, right? So, and there aren't any double bonds or triple bonds. So, and there aren't any other things on here except for some side groups. So this is going to be pentane. So I would go ahead and write down pentane at this point. And then what we have to do is we have 3 we have 3 side chains. They're all methyl, so we're going to have a trimethyl pentane. But the question is, would it be 2,2,4 trimethyl, or would it be 2,4,4? The answer is we want it to be 2,2,4. So that means we want to start numbering over here on the left-hand side. So this is carbon 1, so this is carbon 2. And so we've got 2 methyls on that one, so we've got 2,2. And then over here on carbon 4, we have another methyl here that's not on the main chain. So 2,2,4 trimethyl pentane, which is answer choice D. Next slide. Next slide. How are the following compounds related? Well, so let's just take a quick look. They both have 2 carbons, 1 oxygen, and 6 hydrogens. So they're the same chemical formula, but their structure's different. They're attached differently. So when we have a situation like that, we call these structural isomers. So our answer choice here is going to be just C. Next slide. Next slide. The next one is a an alkene. So when we do our longest chain for this one, we want to include the alkene. So it's 1, 2, 3, 4, 5. If we went the other way, we would have 1, 2, 3, 4. So we don't want to do that. So the longest chain is 5. So it's pentane, which changes to pentene because it's got the double bond there. So it's pentene, and it's 1 pentene because the double bond starts on carbon 1 here. So it's going to be a 1 pentene. So you can go ahead and write that down And then there's just this one side group on the 2-carbon, and it's an ethyl. So it's 2-ethyl, 1-pentene, and that looks like answer choice D here. Next slide. Next slide. The following compound, name it. Okay, so we have to count our carbons. This is going to be an easy one because there are no side groups. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would be no name if it were an alkane, but it isn't. It has a triple bond here. You have to be careful. So that's not a double bond, it's a triple bond. So that means it's an alkyne, so it's no-9. N-O-N-Y-N-E. No-9. And then we have to put the number of the carbon where the triple bond starts. So it's going to be 1, 2, 3. Now we could start at the other end, but the number would be larger. So it's just going to be 3, no 9. Answer choice D. Next slide. All right, next slide. We're almost finished. Not only with this, but with this chapter also, and also with the class. 2 methods of producing polymers are, and I'll let you look at this, guess at the answer, see if you can get it. We talked about it earlier, and I'm just going to go ahead and show you the answer. And next slide. Polysaccharides, proteins, and nucleic acids are all examples of, and I'll let you look at this one and answer it. See if you can guess it. If you need to, you can pause it here. I'm going to go on to the answer. And then the next slide. And then the functional group denoted by something like, for example, carbon, O carbon is known as an ether. It's an ether. So if you had, for example, if you had CH3O, CH3, then you would have a methyl. I'm not going to draw the H's. You'll forgive me. So it would be CH3O, CH3. That would be called dimethyl ether because you've got methyl on both sides. Next slide. So it's known as an ether. Next slide. And I think we're done here. All right, well, that wraps up our class. I enjoyed having you guys while we were in the classroom portion very much. You're an excellent class. Your grades are absolutely outstanding. My problem is that your grades are actually too good, but we'll figure something out. But anyway, so that wraps up exam 4. And as I said before, it's actually going to wrap up the complete class. So good luck to you. Good luck on the final. If you ever need anything, don't hesitate to call or email, and maybe I'll see you around.